Okay, so this is our next video on Chapter 3 for Math 1560, Calculus 1 at U of L for fall 2017. And in this video we're going to look at concavity. So this is section 3.4 in Chapter 3. And we're just going to do a quick summary of the basic ideas in 3.4, and then as usual we'll work through the relevant examples in class. So if you have a differentiable function, in the previous video we looked at the fact that if the derivative is positive or negative, then we get some information about the function, the original function, whether the original function is increasing or decreasing. Concavity has to do with whether the derivative is increasing or decreasing. There's an alternative definition, and let me kind of, we'll draw the pictures that kind of give you the idea of what it looks like. So if your function is concave up, right, that means that the derivative is increasing, so the value of the slope is going up. So you have something that looks like that. Okay, this is concave up. And if your function is concave down, that means the derivative is decreasing, so the slope is getting smaller. And so you have something that looks like that. Okay. So these are the two kind of pictures that you have in mind when you think of concave up, concave down. The other way of characterizing concavity is that for concave up, whenever your graph is concave up, the tangent line always lies below the graph. And for concave down, the tangent line at any point where your graph is concave down, the tangent lies above, right? And so we can see that in these pictures. If you choose any point here on this graph which is concave up, and you draw the tangent through that point, you can see that that tangent line is lying below. And similarly for concave down, if I draw the tangent line, let's say here, right, we can see that the tangent line is above. Okay, and so one way to think about concavity, right, it's the departure of the derivative from being constant, right? So if the derivative is non-zero, we know that our function isn't constant. But if you think about, kind of a basic linear function, right? If we think about, just f of x equals kind of m times x, mx plus b, let's say, right? A basic linear function, we know that the derivative is a constant. And of course the graph is just a straight line with a particular slope. If m is positive, it's increasing. If m is negative, it's decreasing. But we have a straight line. Now, concavity measures the tendency of your graph to curve. So it measures kind of how far away your graph is from being linear. How far is it away from being a line? And right, so if your derivative is changing, then you're going to deviate from a straight line. So if the derivative, if the derivative is increasing, that means the slope is getting bigger, and that means you're going to curve away and up from the line, right? So if the slope gets bigger, you kind of head up this way. If the slope gets smaller, well, then you're going to head down that way, right? So this is the other way of thinking about concavity, right? In terms of where the tangent line is relative to the graph. Okay, and you might guess that, well, since the first derivative is a function, and we know that the derivative of a function tells us whether we're increasing or decreasing, well, the derivative of the derivative will tell us when f prime, right? So f double prime is going to tell us when f prime is increasing or decreasing, right? Because if f prime is positive, then we know that, or if f double prime is positive, well, we know that that means that f prime is increasing, right? That was the topic from 2 videos ago, right? Because remember that f double prime is the derivative of f prime. And if f prime is increasing, that's exactly what we defined concave up to mean. And similarly, if f double prime is negative, Well, that means that f prime is decreasing. And we know that's what it means for our graph to be concave down. Okay, and of course, one of the things that would be of interest if your graph is going to switch from concave up to concave down. So if your first derivative is going to switch from increasing to decreasing, meaning that the second derivative is changing sign from positive to negative or from negative to positive, then you have what's called a point of inflection, right? So a point of inflection is somewhere where your graph is switching from, say, concave up to concave down, and there's some point in between where it switches between being concave up and being concave down. There's somewhere there where if you drew the tangent line at that point, right, it's neither above nor below the graph. So there's kind of a point there where the graph kind of looks linear for a short period of time, right? Or maybe you switch from concave down to concave up, and again you have some point where that switches from being concave down to concave up. So these are what points of inflections look like. Sometimes you'll think of these, you'll hear these referred to as, these are your points of diminishing returns. If you're thinking of functions in kind of context of maybe economics or finance or something like that, right? Where when your function is concave up, when your graph is concave up, that means that increasing x is increasing f prime, and so the rate at which your function is increasing is also increasing. So putting more x in makes your value go up, and it makes it go up faster and faster and faster. And then once you hit that point of inflection, well, putting more in still increases the value, but it doesn't increase it as much as it was before, right? So now you continue to increase the value of f, but f prime is getting smaller, so the rate at which f is increasing goes down, and so you kind of have this idea of diminishing returns, that the value of f is going up, but it's not going up as fast as it was before. And of course, you can reasonably guess that this point of inflection, if the second derivative is changing sign, that's going to be somewhere where the second derivative is either 0 or does not exist. Okay, and so then you can do the same sort of thing that we did with increasing, decreasing, and with critical points. We can find the places where the second derivative is 0, and then we can set up our sign diagram, and we can determine our intervals of concavity, where things are concave up or concave down, right? So here's a function, f of x. We want to work out these intervals of concavity. And so, of course, we need not just the first derivative, but the second derivative. But before we can get to the second derivative, we need the first. So what's f prime? Well, quotient rule says we do derivative of the top. So 6 times the bottom minus the top times the derivative of the bottom, 2x, over the bottom squared. Okay, so this gives me, so there's going to be 6x squared minus 12x squared, so, and then there's a 6. So overall I get 6 minus 6x squared over x squared plus 1 squared. Okay, so there's the first derivative, and now I can continue on. I can get the second derivative, and of course that's going to be quotient rule again. So f double prime, we do the derivative of the top, we get minus 12x times the bottom, x squared plus 1 squared, minus the top, 6 minus 6x squared, times the derivative of the bottom there. We'll use chain rule, so 2 times x squared plus 1, times the derivative of the inside, so we get 2x, all over x squared plus 1 squared, so now it's to the 4th power. Okay. Now we got to clean this up. We got to simplify. One of the things that you want to be careful of here, one of the mistakes that's easy to make when you're dealing with these, when you're taking higher derivatives of rational functions, don't expand that denominator. Leave it like that. Leave it factored. Leave it as a power, because you're going to find simplifications. And notice that both of these terms have at least one copy of x squared plus 1 in them. So if I factor that out, x squared plus 1, what am I left with? I've got minus 12x times x squared plus 1 minus 6x squared times 4x, and all over x squared plus 1 to the 4. And now, of course, you can cancel this one with one of those ones on the bottom, leave you with 3. And what do we have if we expand things here? We've got minus 12x cubed minus 12x, minus 6 times 4x minus 24x, minus 6x squared, that's plus 6x squared, times 4, that's 24, plus 24x cubed. So if we simplify 24x cubed minus 12x cubed, we've got 12x cubed minus 12x over x squared plus 1 cubed. So let's factor. Take out a 12x, we're going to be left with x squared minus 1. We can factor that as x minus 1 times x plus 1. Jumping one step there because I'm running out of space. But you guys can fill in the missing steps. Feel free to pause the video and verify the missing steps that we can factor down to where I just got to there. Okay, so now we've got the second derivative, and so we need a sign diagram. What is it going to look like? Well, we mark our zeros, minus 1, 0, 1, and again, if you work through the signs, the bottom is never negative, right? We don't have to worry about the denominator because x squared plus 1 is always positive. And so we just have to worry about the signs, excuse me, in the numerator, and we get to there. Okay, so now we can see that we have 3 inflection points, right? Minus 1, what's f of minus 1? 6 times minus 1, that's minus 6, minus 3. If I put in x equals 0, 0, 0, and then 1, 3 are my inflection points. And I see that my function is concave up. Let's just write CU because I'm short on space. Concave up on minus 1, 0, union 1 to infinity. And it's concave down on minus infinity to minus 1, union 0, 1. Okay. Now we've determined those intervals of concavity. One of the things we could have done, I didn't do it, but if we were interested in, let's say, actually going all the way through and determining, let's say, a graph for this thing, I could have come back up here, right, and I could have also worked out the sign diagram for f prime and determined the critical points and gone from there. Okay, so you'll want to make sure you check my work on this, make sure I didn't make any mistakes. And oh, I can see already, you know what, guys, I did make a mistake, right? Where is my mistake? Minus, yeah, do you guys notice? Minus 20, minus 12x, minus 24x. Okay, you guys have been probably screaming at the screen this whole time, telling me that that should have been a 36, right? So then, what is this? This is going to be 12x times x squared minus 3. Oh boy. Okay, so now I gotta do some fixing here, right? At 12x, I should have x minus root 3 times x plus root 3. So, by the way, the thing that got me worried here, in case you're wondering, you'll notice that the critical points from f prime, the critical points are when x equals either plus 1 or minus 1, right? We can see that up here. The critical points sometimes they can coincide with the inflection points, but not usually. So when I got those same x values for both of them, I got a little bit worried. I said, okay, I've done something wrong. I better go double check. So now I know that should be minus root 3 plus root 3. So this should be root 3, root 3, root 3, root 3. And then I'd have to adjust this as well, right? So what are my inflection points? My inflection points are going to be, well, when x is minus root 3, then I'm going to have 6 root 3 over 4 minus 6 root 3 over 4, 0, 0, and then root 3 and 6 root 3 over 4. Those are my inflection points. Okay, well, we caught that before we ended the video, so all is not lost. If I had better editing software, I would just cut that part out and you guys would never know that I messed up. But yeah, it's probably good for you to see that mistakes happen and you can fix them. All right, so that's it for concavity.